Chapter 53, Organization of the Respiratory System. So when we talk about respiration, the main function of respiration is to provide oxygen to the tissues and remove carbon dioxide from the tissues. So the four major components of respiration are, first of all, there is pulmonary ventilation, which means the inflow and outflow of air between the atmosphere and the alveoli. So after the air has reached the alveoli, it needs to undergo diffusion. Okay, so then there is diffusion of oxygen and carbon dioxide between the alveoli and the blood in the capillaries that surround the alveoli. And then after the diffusion has occurred, there is transport of oxygen and carbon dioxide in the blood and body fluids to and from the body's tissue cells. And then there is regulation of ventilation and other facets of respiration. So the respiratory system in humans, it involves the following structures, that is the lungs, the conducting airways, including the oral and nasal cavities, the nerves that control respiration and the respiratory centers in the CNS, and also structures involved in moving air in and out of the lungs, such as the rib cage, the intercostal muscles, the diaphragm, and the abdominal recti, that is the abdominal muscles. So when we talk about the lungs are the organs for respiration. There are two in number. We have one right lung and we have a left lung. There are 3 lobes in the right lung and 2 lobes in the left lung. And then the lungs are lined by the visceral pleura, which is separated from the parietal pleura by a pleural space or cavity, which is filled with pleural fluid. And then when we talk about the trachea, it branches into 2 main bronchi, and each bronchus branches further into lobar bronchi that connect each lobe of the lung, and finally these further branch out into segmental bronchi and into smaller branches till they become the terminal bronchioles. That is, they are the smallest airways without any alveoli, the terminal bronchioles. So there is a model called as Weber's lung model, in which whenever there is branching in the system, in the tracheal system, we call it a generation. So generation 0 to generation 16 is called the it is called the conducting zone, okay? Whereas 17 to 23, it forms the respiratory zone. So this is called the conducting zone. And then when we talk about the what happens after the terminal bronchioles, they are further divided into respiratory bronchioles. They differ from the terminal bronchioles because they have alveoli attached to their walls. Okay. When we talk about a respiratory unit, okay, let's see here. Okay, this right here is a respiratory unit. All right. Okay, so you can see that it is composed of a respiratory bronchiole, the alveolar ducts, and the alveoli. There are about 300 million alveoli in the 2 lungs, and they're surrounded by extensive vasculature. So it's as if the alveolar wall has been described as a sheet of flowing blood. Okay, this permits that it favors gas exchange. And when we talk about the respiratory membrane, so as you can see here, for epithelium, we always need it to rest on an underlying basement membrane. So draw the basement membrane on both sides and interstitial space in between. And here draw the alveolar epithelium, okay? And then the fluid and surfactant layer over the alveoli to reduce surface tension. And over this basement membrane, draw the capillary endothelium. And here you have your RBCs, and diffusion of gases takes place through this membrane. Okay, this is the respiratory membrane. So the total surface area of the respiratory membrane is about 70 meters square in the healthy adult human male. And the total quantity of blood in the capillaries of the lungs at any instant is 60 to 140 ml. So this small amount of blood is spread over the entire surface of the lung, that is 70 meters squares. So that is why it is easy to understand how easily the gases they diffuse through this membrane. So when we talk about the laws that are applicable in respiratory physiology, we have the Boyles Law, in which P1V1 is equal to P2V2. Remember it like this. Boiling refers to temperature, so T is constant. So in the ideal gas equation where PV is equal to nRT, if you take out T, you have P1V1 equals P2V2. And then you have Charles' law, You can remember it like this. Prince Charles was always under a lot of pressure. Okay, so keep pressure constant. Then you have V by T equals is a constant. Okay, V1 by T1 equals V2 by T2. Then we have the ideal gas law, which says PV is equal to nRT. And then the Avogadro's law, which says under same conditions of temperature and pressure, so cancel out T, cancel out P, you have that equal volumes of different gases contain an equal number of molecules. And then we have the Daltons Law, which states the Daltons Law of partial pressures, which states that the sum or the total pressure exerted by a gas is equal to the sum of the partial pressures of the individual component gases. Okay. And then we have Henry's law, which states that at constant temperature, the amount of gas that dissolves in a liquid is directly proportional to the partial pressure of the gas with which the liquid is in equilibrium. And then we have Graham's law. Graham's law states that the rate of diffusion of a gas is inversely proportional to its molecular weight. And finally, we have the Fick's law. We are acquainted with this equation. That is the concentration. The net diffusion rate is equal to area into coefficient into the concentration gradient or the difference in partial pressure divided by the thickness of the membrane. So D is a constant. It depends on the solubility of the gas and is inversely proportional to the molecular weight. So D is directly proportional to solubility, inversely proportional to the square root of molecular weight of the gas. Then the respiratory system also has certain non-respiratory functions. That is, the lungs, they have non-respiratory functions which include filtration functions. So in the nose, what we have certain hairs, right? The hairs at the entrance to the nostrils, they are important for filtering out large particles. And more importantly, there is removal of particles by turbulent precipitation. So we have the conchae, right? The internal nares and all that. So they're all curved. So each time when air hits these obstructions, air can pass through. It changes its direction of movement, but the particles that are suspended in air, they can't change their movement and they undergo turbulent precipitation. And the particle size that undergo turbulent precipitation are usually 6 micrometers. Okay, this is because the particles suspended in air have more mass and momentum than air, and they cannot change their direction of travel as rapidly as the air can. And then when we talk about the size of particles entrapped in the respiratory passages, 6 microns, they enter the lungs. They cannot enter the lungs through the nose if the size is greater than 6. And of the remaining particles, between 1 and 5 microns, they settle in the smaller bronchioles as a result of the effect of gravity, that is gravitational precipitation. Okay, so terminal bronchiolitis disease is common in coal miners because of settled dust particles, all those carbon particles and all that. So some of the still smaller particles, less than 1 micron, they diffuse against the walls of the alveoli and they adhere to the alveolar fluid. And even less than 1, that is 0.5. So they remain suspended in the alveolar air and they can be expelled by expiration itself. And particles of cigarette smoke are about 0.3 μm. Okay, so almost none of these particles are precipitated in the respiratory passages before they reach the alveoli. And there are certain immune functions as well in the respiratory system. So large number of tissue macrophages that are present as integral components of the alveolar walls. They can phagocytosize particles that become entrapped in the alveoli. So they are removed by the alveolar macrophages and others are carried by the lung lymphatics. So if the particle size is large that it is not digestible, macrophages, they often form a giant cell capsule around the particle in such time. So when the cell capsule is formed, the foreign particle, it can be slowly dissolved. So such capsules are frequently formed around tuberculosis bacilli, silica dust particles and even carbon particles. Lungs also have metabolic functions, that is angiotensin 1 is converted to angiotensin 2 by angiotensin converting enzyme ACE present in the surface of the endothelial cells, and serotonin is metabolized by the endothelial cells after being internalized into the cell. And then we have vocalization and phonation. So speech, it is a sum of the contributions by the respiratory system plus the speech centers plus the respiratory control centers and the mechanical activities. When we talk about the mechanical functions of speech, it includes laryngeal phonation plus articulation. So what is phonation? It refers to vibration, okay? So the larynx acts as a vibrator. It is called the sound box. The vibrating elements are the vocal folds, which are commonly called the vocal cords. So as you can see here, this is a picture of the vocal cords. You can see. So during phonation, the cords, they move together, okay? So that the passage of air between them will cause vibration. The pitch of the vibration is determined by the degree of stretch of the cords, but also how tightly the cords are approximated to one another and by the mass of their edges. And also there are slips of muscles between within the vocal cords, which can change the shape and masses of the vocal cord edges, okay? And then there is articulation and resonance. The resonators include the mouth, the nose, the associated tissues, the pharynx, and even the chest cavity. The function of nasal resonators is demonstrated by the change in voice quality when a person has severe cold that blocks the air passages. Okay. And finally, the respiratory system, it is also involved with acid-base balance, that is, it eliminates CO2 from the body.